Hey Calculus, we're going to work through 7.6. We'll see how long this video takes me. And we're going to examine how we can find volumes of any kind of shape. Like we can find this oddly shaped, sometimes we call them vases or something like that. And what we're doing is we're revolving this figure around the x-axis. So the main premise with this is that we've learned that we can use integration to find the area under this curve. So what we'll be doing is thinking about, okay, well, what if we did something special to this? And that something special would be revolving. So imagine for a second, and I'm trying to draw this in 3 dimensions, which is why I'm glad we have this visual right here. And we were to rotate it around this axis, and what you would see is we would have an infinite number of circles. So let me draw another one right here. I'll just draw another one kind of the same shape as the first one because it has the same height. And then this last one, you can see how large that circle is. Now you do have to use your imagination. This is not necessarily an easy concept just to see it and be able to understand. But what we have is, instead of an infinite number of rectangles inside of this figure, we have an infinite number of circles. But if you notice that the area that we found, and I am talking about the area under the curve, those are just a bunch of radii. So there's like an infinite number of circles, and then the area under the curve that we've learned is equal to those infinite number of radii. So the whole premise is, if I wanted to find the volume of this shape, I guess I'm talking about this shape now, is what I can do is find all the infinite number of circles by using a formula. Well, this is the one that we're actually going to use because we don't have to concern ourselves with h, because the h is represented by the integral of every one of these. So notice that the formula that we're talking about is the radius. So as we do the formula of the sum of all the disks added together, that's the sum is represented by the integral. But notice that the formula for this problem is pi times the radius squared. Now, why does he talk about this axis of rotation? Is we don't have to revolve around the x-axis, but if you do revolve around the x-axis, then y equals 0. So the axis of rotation here would be 0, whereas if we shift up a little bit, we'll have smaller radii. And so the whole premise there is that, well, we can take away is essentially what's happening. So if we have the x-axis, if we're revolving around the x-axis, then the axis of rotation would be y equals 0. Well, what's anything minus 0? Well, it's that thing. So how that changes would be if we shifted the graph up or down any. And then this other one is just moving the pi in front because pi is a constant. So that's typically how we write it. So by the way, this is called the disk method. You don't have to know what it's called, but that's what it's called. Whereas sometimes what we do is maybe we want a base, and a base has a hole, and a space in between. So what we might have, and this problem just says y equals c right here. I don't know if it shows up on your page. But we might revolve around the x-axis still, but we want this empty space. So what happens is, you got to use your imagination because I'm not the best at drawing, is I might rotate the outer function, but then I want a cylindrical space in between. So what you want to do And it is still the same thing. It's pi times the integral, because we're summing all of these areas together. But what you want to do is take the outer function minus the axis squared. So that finds this volume, I guess I should say area. And then we're going to subtract off this area, and it becomes volume because we're adding all of these areas together. This is called a washer method. If anybody's familiar with like the tool that's a washer, almost looks like a donut. If you've ever seen that, it's called the washer method. If you open up a math textbook, they explain it this way. I think though it might be best if we just examine this through an example, and then go on from there. How about this? Before I do this, my kind of shortcut of doing this, when to do the disk method versus when to do the washer method, is if your entire function is touching the axis that you're rotating around, then it's the disk method. But if you're rotating around an empty space, so I'm trying to highlight, we have this empty space between the axis we're rotating around, then you're going to use the washer method. So as I do these problems, you'll either see me right away write one thing squared or two things squared based off of what the graph would look like. So I wanted to mention that. I'll probably mention that in class as well. And if you're confused, write the question down and then come to class and ask me. And they usually give you a picture. So that's pretty nice. They usually give you a picture. So if we consider the graph below, we have the quadratic and we have this linear function. So find the volume that's of the solid when it's rotated around the x-axis. So what I was just mentioning is, do you see how there's blank space between the area we're considering and the x-axis? If your answer is yes, there's some blank space in here, that's my clue that we're going to do the washer method. Now, just a heads up, sometimes they will not give you these points of intersection. So if they do not give you those points of intersection, you have to find those points of intersection. Well, that's pretty easy because they're both already y equals. So you can find the points of intersection. Let me write that down. By setting the equations equal to each other. So x squared has to equal x plus 2. And then that's a quadratic. This is why you spend a lot of time in Algebra 2 and pre-calculus, factoring x minus 2, x plus 1. So you can deduce then that your volume formula will be pi from your bounds of negative 1 to positive 2. And as I mentioned, this is the washer method because of the blank space. I'll even change colors though. Again, if you're confused what I mean by blank space between the area we're finding and the axis we're rotating around, that's my thought bubble, then please write down that you have a question and you want to ask. So the washer method tells me that I need two separate functions being squared in terms of x. So what's the function that's further away? The function that's further away is the linear function. By the way, you don't always have to prove it, and usually it doesn't matter because we're squaring the piece. So we have x plus 2 that's being squared. And then, by the way, I do technically have a minus 0 in here, but because we're rotating around the x-axis, which is the equation y equals 0. So we don't usually write in that minus 0. But if I go back to the formula where it says, minus the axis that we're rotating around, well, then we're good. And then the other function, the one that's closer, the lower function, is the x squared function. And again, you could write minus 0, the axis we're rotating around, but we don't need that. So what I typically do, especially if this is a no calculator problem, is I would go ahead and FOIL this piece out. And that, to me, makes the algebra, the finding the integral a little bit easier. We're looking at 1/3 x cubed plus 2x squared plus 4x minus 1/5 x to the 5th from -1 to 2. I don't know if this would be a calculator or no calculator, but some of the math is not that bad. Especially 2 cubed, not that bad. That's 8. So we're looking at 8/3 plus 2, 4, 8 plus 2, 4, 8. 2, 4, 8, 16, 32. And then subtracting off, I should put maybe an extra bracket in here. -1 when you cube it is still negative. -1 when you square it is positive, though. Negative, and then -1 to the 5th power is negative, so that's going to change that to plus. If I saw a problem this difficult, though, I would probably anticipate using a calculator, because getting the same denominators, you'd have to have a 15 there. So I'm going to jump to the answer key. So I trust you can use a calculator. This guy talks a little bit more about that. Oh, he even talks about if the axis was lower, he erased the one that he had. I don't know why he did it that way, but that's okay. Apparently this reduces to 82/5 pi. And every time I do this, I see students who will magically drop the pi along the way. Please, please, please do not do that. Okay, that'll make a big mess of your problem. So. And I forgot to write equals over and over again. So 82 pi over 5 would work. I don't believe I have enough time to go through all of these problems in this video. But as we look at this next one, let me explain how to set it up. So now we're going to rotate this axis about y equals 4. So y equals 4 is up here, but there's still blank space between where these two functions intersect. So we're still doing the washer method. My points of intersection are still the same. So we're looking at pi, still -1 to 2, and it's still the washer method. But the difference now is the function that's further away is the x squared function compared to the axis we're rotating around. So what I'm going to do is find the area of all of this. This is how my brain works. Your brain might work slightly different. So what I'm about to find is this area. Oops. And that would be of the formula 4 minus x squared. Now if you notice in the way he writes it is it's x squared minus 4. And the reason why it doesn't matter is we're going to square this piece anyway. So that's why the way my brain works is I write 4 minus x squared. And if you didn't believe me that that's equivalent, go ahead and square it and you'll get 16 minus 8x squared plus x to the 4th power. And then what I need to do is take away, and get a different color highlighter, and I'll do purple, this area. Well, how do I find that area? It's the equation 4 minus the linear function, which was x plus 2. 4 minus x plus 2. But again, as I flip to the answer key, you might want to work through this on your own. He writes the formula a little bit differently because what he does is he always subtracts the axis you're rotating around second. But if you notice in the very next step, because we square it, every negative that we need becomes positive, and it doesn't matter is my point. So I'll see you in the next video.